And sir, please record, sir.
Yeah, I also recorded. Sorry, I forgot to unmute and I was talking from the last time.
Sir, we are not receiving the previous recorded lecture, sir.
The previous recorded lecture was not uploaded. Huh? I will upload it today.
Yes.
Sorry. I will upload it. I thought I have uploaded it, but let me just check it once. Otherwise, I'll upload it immediately. Okay, after the class.
Yes, sir.
Okay, so what I was telling before was in the last class we have looked at FFT size and sampling. Okay, so first I want to ask you if there are any questions on this. Okay, so all of you have understood this part, no? I mean, how do you choose your FFT size and how do you choose your sampling frequency? Okay, so there were some questions on, I mean, I received a few questions specifically when I said that you sample at a higher rate and you put you put zeros here and sorry, you put zeros here and here. There were some questions on what you mean by zeros. Is it bits are set to 0 or what is set to 0? Okay, so I'm going to now just explain this a little bit and show you some piece of code and also show you the spectrum, I thought, and then we'll proceed further. Okay, so you generally have 0 to so many subcarriers. Okay, 0 to 3072 subcarriers or some number of subcarriers less than 4096. Let's just take 3072 for simplicity. Okay, so what you do is, so essentially these are subcarriers are like this. Okay, so some of the subcarriers so this is a PRB grid. This is my PRB grid. Okay. Some of the subcarriers are data. Okay, so data means what you have. You have bits which are then mapped to constellation points depending on size. And once you get to a constellation point A plus Bj, what you do is you put into the subcarriers. Okay, for different subcarriers have different data. Okay. Suppose some of the subcarriers are pilots. Just suppose this is a pilot P1, P2, P0. Okay. What you do is, I mean, this is not generated by data. But the pilots are not generated by data. They are generated by something else. But there's some complex values you just put it there. Okay. And then what we do was, we have the 4096 FFT. Okay, so 4096 FFT has some subcarriers that are there. 4096 subcarriers are there. What we do is, we set all the subcarriers in this 4096 to 0 first. Okay, everything is set to 0. Okay, then we just map this whole array into this array. Okay, so once we map that, I'll tell you exactly how the mapping happens. Once we map that, what happens? Some of them gets, so for example, from here, from here to here, I map this to here, this part. Okay, from here to here, I map it to this part. All the other things are actual zero values. Actual zero values before you take your FFT, before you take your IFFT. Okay, does it make sense? So what? So any questions? So you actually, it's not bits which are mapped to 0. Okay, so when I say 0, you map to something to 0, subcarriers to 0. They're actual. Instead of a complex number a plus bj, you do 0 plus 0j. Okay, so that no power goes in that subcarrier. Does it make sense now? So that is why what happens is these subcarriers are all zeros, actual physical zeros. Okay, whereas these are occupied by pilots and data, or whatever map they're mapped to. Fine. Good. So let me just show you a piece of code on how we do this. So all of you can see my MATLAB? Yeah. Okay. So here the final FFT size is 4096. Okay, I'm taking 273 subcarriers. Okay, so 273 subcarriers, sorry, 273 resource blocks. So 273 resource blocks are the maximum allowed in 100 megahertz. Number of resource elements per PRB is 12. So the number of subcarriers that I can use is L, which is number of PRB into number of resource elements per PRB into 12. Forget about these things for now. Okay, so I'm assuming a sampling rate of 122.88 mega samples per second. So it's a 100 megahertz bandwidth system. Okay, so I'm just doing QPSK for simplicity. Okay, I'm doing QPSK for simplicity. I generate the bits, then I map the bits to symbol, Okay, this is something that you guys, you have all done before. Now what I'm doing is I'm just mapping. I'm just for simplicity, I'm not assuming any pilots. Whatever subcarriers are there, I'm populating all the subcarriers. The L subcarriers. L is 3072 or something. Okay, L is how much? Let me just check 1 minute. 3276 subcarriers. I'm just mapping them to the QPSK symbols. Okay. Then what I'm doing is I have something called final subcarriers. This was the 4096. Final subcarriers is 1 comma n. Okay, it's a 4096 FFT. Sorry, it's a 4096 final subcarriers. So in this 4096, where am I doing this? Okay, what am I doing is I am mapping them to subcarriers. All the other things I'm setting to 0. Okay, this is the map. I'll tell you about this map in a minute. Okay, I'm populating this bigger thing with these subcarriers. Then I'm taking IFFT and I'm transmitting. Okay, I forget about resample. Resample is just I'm oversampling it by some factor. Just hold on 1 minute. Okay, so I'll just put an oversampling factor of 4 so that you can see this easily. Okay. You can see how the spectrum looks now. So if you look at this, only from minus approximately close to, I had to zoom this a bit. Let me zoom this a bit. Okay, it's close to almost close to minus 50 to plus 50, which is 100 megahertz bandwidth. My signal is occupying. Okay, the other things up to minus, all these things are zeros. Okay, of course, this is because essentially this is you can see the sync kind of interpolation happening now. This is because of the slow decay of OFDM. You can see that. Okay, of course, this repetition is happening because I'm doing an oversampling. Forget about the second thing. You can just think about the first part up to this point. After that, it's just repetition. That's I have to do a filtering. I didn't do that, so that's okay. Sir, receiver knows the where zeros are, so that will act accordingly. Yes, of course, receiver exactly knows where those zeros are, so it will remove those things. That map is a fixed mapping. Okay. Any questions before we proceed?
Sir, that extra band can be used by some other user, or it will be kind of waste.
What extra?
That band between minus 50 to some.
Yeah. So no. Remember that we are given only 100 megahertz bandwidth. This bandwidth can be used by some other operator if you want to. Okay. But you should understand that this fall off is that there's interference here, but in actual cellular system, you put a filter also to decrease this further, whatever is this side and this side. Okay, I'm not doing all that in the MATLAB code at this moment. Okay, you put a filter also so that this will this whole thing will get filtered off. Okay, so that you can put one more user here if you want to. Does it make sense?
Yes.
Okay. Any other questions? Okay. So I'll share this MATLAB code with you. So this will also help you in the upcoming assignment also. So you can play around with this code, different sampling rates. Forget about this SNR for now, but there's no receiver, so SNR doesn't make any sense, but I just added that up. You can play around with the different PRBs and other things and see how the spectrum and other things look. Okay, you can increase the modulation also. You can make it 16 QAM also and other things. It will still work. The whole code works. Fine. Play around with this. Okay. So now let's go forward and look at cyclic prefix and other things. Okay. So the cyclic prefix, so essentially which document gives you the cyclic prefix? Again, the document on 38211 gives the cyclic prefix. I'll just open the document and keep it ready. Okay. So we finished all this. So there is this something called as OFDM baseband signal generation 5.3, section 5.3. Okay? So in section 5.3, they tell you, so this, remember, so let me zoom it a bit so that people. Okay, this is the final formula. See, in this whole thing, they will not tell you to do FFT, they will not tell you to do IFFT and other things in the specification. Okay, what they say is, see, remember AKL P comma mu. AKL was the value in the K comma Lth point in the grid for a port P and U subcarrier spacing. Okay, they say that if this is there, then how do you generate the output baseband signal? Okay, they give a formula for this. Okay, it turns out that you can interpret this formula as an IFFT. It almost looks like an IFFT, except there's lots of other terms. Okay, so these terms are the shift terms. These are the mapping. These terms exactly give you the mapping from this 3072 or 3726 into this 4096 grid. How do you do that? Okay, so I will just give you a formula for that, so that's easy to use. So I simplified all this to get through the formula. But this tells you how to do this thing for different values of mu and mu0 and other things. Okay, if you have multiple subcarrier spacings in the same grid, how do you put that? Okay, let's not get into that. Effectively, this is an IFFT done in a very specific manner. Fine. So they do, see, remember one thing in a specification, they never tell you how to implement it. Okay, so they don't tell you to implement this using IFFT. They just give this formula and they leave it to your imagination. You can do whatever you want, except that the output should look as compliant to this particular formula. Fine. Okay. So they say that the time of this OFDM symbol is from some start to the same start plus NU plus NCP LMU. Okay, so where the NU is the length of this whole sequence that they give it here. We'll do this completely. We'll do this whole thing, and the cyclic prefix length. The cyclic prefix length is given here. Okay, remember the cyclic prefix length is given here. We will just now see, we'll understand how to interpret the cyclic prefix length. Fine. Okay, I just wrote this formula. Okay. Okay. Sorry. Okay, this is what I wrote there. So it turns out, see, it's specified in terms of K. K, remember K. What does it say is the cyclic prefix length, the time duration of the whole OFDM symbol is N mu, which is the number of normal symbols plus cyclic prefix length into TC. Okay, so whatever they gave here, you should multiply by TC to understand the cyclic prefix length. Okay, so the cyclic prefix length, if you compute these formulas, remember what was kappa. Okay, kappa was what? Kappa was something that we have done in the first thing. Kappa is TS by TC, which was 64. Okay. Okay. So if you do that, it turns out this is, so it turns out that there are two types of cyclic prefix. Forget about extended cyclic prefix. In the normal cyclic prefix also, remember what was our L? Maybe I'll zoom into this formula so that you can see. Okay, remember our L was the OFDM symbol. Okay, let's just stick to mu is equal to 1, which is 30 kilohertz subcarrier spacing. Okay, so if you stick to 30 kilohertz subcarrier system, what it says is, even for the normal cyclic prefix, there are two types of cyclic prefixes. One is 144k into 2 power minus mu, and another is 144k into 2 power minus mu plus 16k. Okay, so this particular plus 16k is there only for the OFDM symbols number 0 and L is equal to 7 into 2, 14. 0 and 14 has this. Okay, whereas the other cyclic prefixes, the normal smaller cyclic prefix is there for all other OFDM symbols. Fine. What does this mean? Okay, we'll do that in a minute. Okay, I'll show you the pictorial, then it will become very clear. Okay, so what is the standard cyclic prefix length? It turns out that your OFDM symbol for 30 kilohertz subcarrier spacing is 33.33 microseconds approximately. Okay, and your cyclic prefix length is 2.34 microseconds. And you can see that as as the subcarrier spacing is increasing, the mu becomes 4. The cyclic prefix length is decreasing. Of course, the time also is decreasing because you understand that it's 1 by delta F. Fine. Does it make sense to you? So now let us do the effective time duration of the OFDM symbol with cyclic prefix. Okay, let's just do this computation once. Okay. So let us focus on the 30 kilohertz and 100 megahertz subcarrier spacing. Okay. So when we focus on the 30 kilohertz subcarrier spacing and 100 megahertz bandwidth, remember our sampling time was what? Our sampling time was 16 TC. This is what we calculated. 16 TC was nothing but 122.88 megasamples per second. Okay. So the total time is equal to 16 TC into 4096. 4096 was the FFT. Okay. So if you put the value for TC 1 by 148 E3 into 4096, you get 33 microseconds. Okay. Cyclic prefix time, if you see cyclic prefix time, it's 144 into K into 2 power minus mu into TC. Okay. So that's what I put. I put 144 into K, which is 64, divided by 2 power minus mu. Okay, by divide by 2 into 64 into TC. So this, if you simplify this expression, you get 2.34 microseconds other than the 0th and the 14th OFDM symbol. Fine. Similarly, you can calculate this for the other subcarrier spacings and other, bandwidths. Any question on this?
Do we have different formula for symbol 0 and 14?
Symbol 0 and 14, it is the same thing plus 16K, 16 into 64. Okay, I will tell you exactly. Once let's see this diagram, it will become very, very clear. Okay, so I'm drawing this for 30 kilohertz subcarrier spacing and 100 megahertz bandwidth. So remember, for 30 kilohertz subcarrier spacing, there are one slot is 0.5 milliseconds. Okay, and there are 2 slots per frame, per subframe. Sorry. Okay. The sampling rate is 122.88 megasamples per second. There is 16 TC. FFT size is 4096. The maximum number of useful subcarriers was 3276, 273 subcarriers. Okay. So what happens is, if you compute this formula in terms of TC, let's compute this formula in terms of TC. How many subcarriers are there? I'm just showing you my, it is 140, let me just write it down and then we will do plus 16. Okay, so 144 into 64 divided by 2 plus 16 into 64 TC is the length of CP. This is what is given by the spec. This is the length of CP for 0 and 14th OFDM symbol. Okay. What was our in terms of number of samples? If you want to find out in terms of number of samples for the 100 megahertz bandwidth and other things, 100 megahertz bandwidth and the 30 kilohertz subcarrier spacing, our sampling rate was 16 TC. Our sampling, the time duration is 16 TC. Okay. Then what happens? TC gets cancelled. TC gets cancelled. If I simplify this, 16 goes 4 times. So it's 144 into 4 divided by 2 plus 16 into, plus 64. This is 288 plus 64. So 352 samples are there for the 0th symbol and the 14th symbol. For all other things, what will happen is this term will not be there. This term is not. This term is absent. So that other symbols have only 288 as the CP length for other symbols. Fine. Did you understand how to compute this? Does it make sense? So this is what exactly I'm actually showing you here. Okay. So they put 352 here. That was our first thing that we computed for the 0th OFDM symbol. For all the first, second, up to 13th OFDM symbol is 288. 288 is the CP length. Again, this is the 14th OFDM. So 13 OFD, I mean 0 to 13 OFDM symbol, that is 14 symbols, make the first 0.5 milliseconds, which is one slot. So at the beginning of every slot, you have a different cyclic prefix. The first symbol, the first OFDM symbol, the 0th OFDM symbol of every slot has a different length of the cyclic prefix, and all the other symbols have a different length of the cyclic prefix. Okay. The reason they did this 352 is so that it fits in this 0.5 milliseconds exactly. Does it make sense?
So again, you repeat this part.
Okay, fine. So what did we see here? It says a cyclic prefix. I mean, let's focus on the normal cyclic prefix. Okay. So this tells, the top thing tells 2048 into k into 2 power minus mu. Tells you the, let's do that computation also 1 minute. Just let me just 2048 k into 2 power minus mu. Okay. This into TC is the time duration. Okay. Divide by, so let's just write this up first. This 2048 into 64 divided by 2 into TC. Okay. This divided by 16 TC gives you the number of samples because we are sampling at 16 TC duration. Okay. So this is nothing but 2048 into 64 by 32, which is 4096. Okay. So in terms of samples, the OFDM symbol length is 4096. That's what it tells. That's what this particular expression tells. And the CP, what CP has two clauses. One, it says is L is, remember, L was the OFDM symbol number. When L is equal to 0 or L is equal to 7 into 2, mu is 1 for 30 subcarriers, 30 kilohertz subcarriers basically. Okay. For L is equal to 0 and L is equal to 14, you have a different cyclic prefix length. Whereas L is not equal to 0 and L is not equal to 14, you have a different cyclic prefix length. Okay. So that is what we come.
Sir, what is the reason for having different cyclic prefix
length? So main reason is if they put 288 here, then this 14 OFDM symbols will not become 0.5 milliseconds. Okay, it will be a little bit short of 0.5 milliseconds. So to make sure that this one slot fits in exactly 0.5 milliseconds, what they did was the first OFDM symbol has a little bit longer CP. Is this clear? See, if this was 288, what happens is if this was 288, then there will be small gap of 64 TS, 64 into 16 TC. That much gap will be there between two slots. To avoid that, what they did was they just extended the the cyclic prefix of the first OFDM symbol. Okay. So the things that you should remember is, in a slot, this is a slot. In a slot, always the first OFDM symbol will have a little bit longer cyclic prefix compared to all the other symbols in the slot. Okay. And I have computed this. I mean, any questions before I go to the next slide and we do this for the other numbers?
So some of the papers say that this also facilitate transition from upload to download.
Uplink.
Yeah, uplink to downlink. Whenever transition happening, so there you have the first CP length slightly bigger.
That's also a valid reason. So that's also one valid reason. But I mean, yeah, it can also be used. But the thing is, I mean, the transition may not happen at every slot, but whenever it happens, it might help you. Okay, certainly it helps you. No. I mean, that's actually an excellent point, actually. Okay, so they have some little bit more duration so that you can do the transition. We will do that again. I will tell you that what happens when it's doing the transition. Okay, but the main thing is now this pakka fits in this 0.5 milliseconds. That was the most important thing. That's why even this was there in LTE before also. I mean, only the first OFDM symbol always has the higher CP length. Any other questions?
Sir, reason for higher CP is not still clear, sir.
Okay. See, if I make this 288, what will happen is the length of the first 14 OFDM symbols from here to here will not be 0.5 milliseconds. It will be slightly less than 0.5 milliseconds. Yes?
Okay, sir.
Okay. So to make this exactly fit in 0.5 milliseconds, they made this 352.
Okay.
Okay, that is one of the main reasons. In addition, like Mr. Ashok Kumar pointed out, this also helps in the downlink uplink transition, a little bit in the downlink uplink transition. Okay, we'll come to that later. Okay, because the downlink uplink transition happens, at least in LTE, used to happen only in between. I mean, in the what do you say, the beginning of a slot, but not anymore. But it does help that a little bit. Okay, so you understood, sir. Essentially, mainly to make this sure that this one slot, which is 14 OFDM symbols, fit in 0.5 milliseconds.
0.5 millisecond. This is the main.
This is the reason. So that's why they increased this to 352. Why that particular number and all that? Because they did the computation and says that if it's 352, it's pakka 0.5 milliseconds. Okay. So if you look at the other computation, let's do a different computation. Okay. So it's 120 kilohertz subcarrier spacing and 400 megahertz bandwidth. Okay. So in 400 kilohertz bandwidth, 400 megahertz bandwidth, this is like what you say FR2. You sample at 491.52 megasamples per second. It turns out that the first CP, I mean the second OFDM symbol, third OFDM symbol are all 288. I think so. I have to just make sure of this once more. OFDM, but the first OFDM symbol has a much more longer cyclic prefix of 544. Okay. And so essentially in this particular case, what happens? 0.5 milliseconds is equal to, so essentially what happens is at every at every 0.5 milliseconds there's a sorry, so I take back my word. So at every 0.5 milliseconds there's a bigger cyclic prefix. That's what you should remember. Not every slot, not at the beginning of every slot, sorry. That is there only for 30 kilohertz subcarrier spacing. For all other subcarrier spacing, what happens is at the boundary of every 0.5 milliseconds, you have a larger cyclic prefix. Okay, that's why it's always at 0.5 milliseconds. At 0.5 milliseconds, you have a larger cyclic prefix. In this case, 544. Okay, I have to do this computation again. I mean, I checked it some time back. It is not exactly matching to 1.125. I mean, maybe one of you guys have to check this once. If this matches to exactly 0.125 milliseconds. Okay. So what are the takeaway points? The takeaway points are at every 0.5 milliseconds, you have a larger cyclic prefix line. Okay. In the 30 kilohertz subcarrier spacing and 100 megahertz bandwidth, which is the most common for FR1, and that's what I'm very used to thinking of slots. At the beginning of every slot, it happens. But in the cases of other things, other subcarrier spacings, what they do is this extra cyclic prefix length is there only at 0.5 milliseconds. Fine. So there's half subframe. It's there.
Sir, sorry, that means in a subframe there will be only two cyclic prefix having bigger length, right?
So in a what? In
a subframe.
In a subframe, if I'm mistaken, is this one. Yeah, subframe. Yes, there'll be two. Exactly two. Yes, this is what a subframe is. So a 0.5, 0.5. So on the beginning one and the half one. Okay. But let me just once confirm this. Let's just do the compute. So essentially for L is equal to 0 for... Yeah, that's true. That's absolutely true. Yeah, correct. What I'm saying is correct. Fine. Any questions? Okay. So just let's recap once what we have done till now. Okay, in terms of the frames and subframes and other things, and then we'll go to the next thing. Okay, so frame 10 milliseconds, subframe is 10 of
Sir, for Prats, it is something different.
Prats is different. Prats is completely different. So when I say that this generation is only for except Prats, Prats is a completely different thing. We'll come when I do Prats. I'll tell it's it's much more confusing. So when we do Prats and the uplink, I will tell you that how it happens. Okay, this is just only for normal OFDM, not Prats, except Prats. Fine. So what are the points we learn? We learn frame has 10 subframes, each of 1 millisecond. Each slot has 14 OFDM symbols. That's more fundamental. And a subframe can have multiple slots depending on the subcarrier spacing. For example, 30 kilohertz, which is the most popular, has 2 slots in one subframe. Okay. Then we talked about a resource element. We talked about a resource element and resource grid. Okay, resource element is the most fundamental unit, and 12 resource elements form a resource block. Okay, that's what we talked. And 381011 gives you the maximum frequencies and the maximum number of PRBs that are there, that are allowed for any given subcarrier spacing and a given bandwidth configuration. Okay. Then we learned about the coordinate system. We talked about something called point A and offset to point A. Okay. We also started looking a little bit about the information elements on how to look at them in 38331. Okay. Then we just got introduced a little bit to the bandwidth part. So essentially, what was bandwidth part? Bandwidth part was nothing but essentially a smaller part of the carrier that is reserved for, that a particular user will be served in. Not reserved, but particular user will be served in. We looked at something called the common resource blocks. Common resource blocks are numbered from the absolute reference point, which is point A. Whereas physical resource blocks are always numbered from the beginning of your bandwidth part, and it's UE specific. So then we looked at FFT size and sampling. So 30 kilo subcarrier and 100 megahertz bandwidth. We looked at different this one. Different numerologies and looked at what should be the sampling frequencies so that we can take the correct size FFTs. Okay. Then we looked at the cyclic prefix today. So we say that cyclic prefix length for 0.7 OFDM, for 15 kilohertz, it's 0th in the 7th, which is the 0.5 millisecond boundary. 0.14 for 30 kilohertz, which is again is the 0.5 millisecond boundary. 0.56 for 120 kilohertz. They have some extra CP length. All others have different CP lengths. Okay. That's what we have learned till now. Any questions before we proceed?
Sir, in that bandwidth part slide, I have one doubt actually.
Sure, please.
Sir, here the bandwidth part 1 is being utilized by 2 UE at the same time. That means there is some overlapping. Because of that overlapping, there won't be any inter-carrier interference or something like that.
No. What happens is, see, what this says is this. So suppose I said this is, so this is what user 1 requested. What the user 1 requested and what was provided by the network. And suppose this was what user 2 requested. Okay. Now, when the base station is serving the UE, what happens is it will not allocate all this to the user 1. Similarly, it will not allocate all this to the user 2. That scheduling is okay. Let me just draw this once. Let me just draw this on a piece of paper. Okay. So this was user 1 BWP. Okay. So this is user 2 BWP. Okay. So now user should schedule. How does user schedule that? What did we learn? We'll use that. It will allocate some subcarriers to user 1, subcarriers to user 2. Okay. What might happen is it can allocate. Sorry, it's not visible. It can allocate this subcarriers to user 1. And it can allocate only this subcarriers to user 2 in the scheduling. So what does bandwidth part say is that this allocation should be in this for the user 1 and this allocation should be in this for user 2. It does not say that the entire thing has to be allocated every time instant. You understood? Chitranjan, is this clear?
Yes, sir. Yes, sir. Yes, sir. True.
It all says that it puts a constraint on the scheduling saying that user 1 should always be allocated here. Similarly, user 2 should always be allocated here.
That means that bandwidth part is only giving the limitation.
Exactly, the limits, the upper and the lower limit in which his allocation should be. But actual scheduling is up to the base station.
Okay.
Okay.
Sir, I have a question regarding cyclic prefix.
In cyclic prefix, sir. Okay.
Actually, not in normal specification that you had taught little earlier, sir, 2 class earlier. There was something extended cyclic prefix, and that was applicable only for
60 kilohertz.
Only for one numerology, that is
Yeah,
60 kilohertz.
Yes.
But others does not support it. Or, so what may be the reason for that?
Okay, so what is the reason for that? Okay, so I think I will explain you that using this slide. Just 1 minute. Okay. See, your cyclic prefix duration. So the reason why they chose 60 kilohertz is mainly to understand. See, your cyclic prefix is a waste of resources.
Okay.
Yes, technically you're not transmitting any new information. There is an overhead. It's a useful overhead because you want to convert some linear to circular convolution, other things. Okay, but it's an overhead. So why did they not do it for any other? Yeah. So one of the main reasons is this one. So so if you are increasing your cyclic prefix, then you are wasting
The resource, wasting
wasting your resources. Okay, that's one thing. And the cyclic prefix length, the wastage of resources. If you think about how much, see, as your subcarrier spacing is increasing, your bandwidth, your OFDM symbol duration is decreasing. Yes. So if you have a larger cyclic prefix, what happens? For as you go to higher and higher subcarrier spacings, then your overhead becomes larger. Yes, because your cyclic prefix length is dependent on this one, on the delay spread. Okay. So because of that, what they thought was, anyway, that's one reason. And the second reason was, anyway, when you go into 120 and 240 kilohertz, mostly you are going to use FR2. Okay.
FR2, yes.
Yeah, and then FR2, you are not going to have too much large cells, and there's not going to be too much of multipath.
Okay.
Okay. So based on these two reasons, I think I can also confirm this. They chose 60 kilohertz subcarrier spacing.
That is the right region, because the small cell, we use the small cell, the distance is very less. In that situation, multipath delay spread is less. And in FR1, since this is the last 60, the last subcarrier spacing, more delay spread, and the time slot is the symbol duration is very less. So for that, I think this is the reason. I think you have rightly said. Thank you, sir.
But let me also confirm this once. Maybe there may be other reasons, but I will find this out. Okay, I think this was the reason, mainly. Any other question? Okay, so let's just look at the spec now. So I think I will stop this today. Tomorrow in the next class, what was it? I'm supposed to. We will do bandwidth part. We will do a bandwidth part. I think not bandwidth part. A little bit of PD and bandwidth part, and then we will proceed to this one. SSB first, synchronization. Okay. So just let me just take 5 minutes and explain you the procedure that happens. So we are going to follow the same procedure in when we do the course also. So initially, when the UE switches on, it searches for some synchronization signals. Okay, it searches for synchronization signals called SS block or the PSS and SSS. Okay? These are some things that are transmitted by the base station. It locks onto these signals. It locks onto the SSS and PSS signals. From there, it estimates the frequency offset, the time offset, and locks onto the resource grid. After this, it decodes something called as MIB and SIB, which is the first control information it decodes. SIB1, system information block, and master information block 1 thing. Once it decodes that, it will know a lot of features about what the network is, what the cell is, where it should transmit pre-ratch, it will know some information. What is the subcarrier spacing? It will know all this information. Then what it does is it will also know patch where it should transmit uplink random access when it decodes the MIB and SIB1 messages. Okay, so then it does something.
Sir, are
like
you showing some other slide?
No, I'm not showing. I'm just telling you the sequence. Okay, then it will transmit patch, uplink patch. Okay, so this patch is a 5-step process. Okay, after the 5 steps are done, then the base station will recognize that is a particular UV, and then it will start allocating resources for the UV in both the uplink and the downlink. Okay, so this is exactly the steps we are going to follow. So first, I'm going to talk about PBCH, which is the broadcast channel, which is the SSB. Okay, we are going to spend time on that. Then I'm going to talk about what are the messages in SIB1 messages and MIB1 messages, SIB and MIB messages. After that, we'll do patch. Then we are going to do what do you say this one? Then we are going to do the data part, the other control channels and the data parts. Okay, so that is what we are going to follow. But before that, in the next class, I'm going to teach you about TED. What are the different configurations that are there? Okay, and how does the uplink downlink transition happen? What is timing advance? What is timing offset and other things? Okay.
One more thing comes in my mind in small cell in millimeter wave by the proper management of the amplitude and phase shifter phase, we can increase the directive gain of the antenna. So in that case, we are increasing the coverage. And I think the multi-path spread, I think that might be very less in that case. So that is also in millimeter wave, the scenario is different. That might be the reason for the CP, the normal CP.
Exactly. So the thing is, millimeter wave is the multi-path. The beams are very narrow.
Very narrow. Just pencil beam.
That's why multi-path. I mean, generally people think of them as almost like an AWN channel with a gain. Almost.
Right.
Yeah, it's very flat channels. Yeah, I mean, but it depends on exact frequency or the reflectors and something. But what you said is absolutely right, sir. That is the reason why they do not consider very large cells. Even if there's a large cell, also there is not too much delay spread.
Right.
Yeah. Okay. So I'm going to stop today. Okay. And in the next class, we will start TDD and bandwidth parts. Okay. I'm going to upload all this presentation till now and the video into the classroom today. Thanks, everyone.
Thanks, sir. Thanks.